Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone, it's my pleasure to welcome Nupur Kothari from University of Southern California. She'll be talking about simplifying the task of building robust and efficient network systems. Her research interests are in systems and networking, and she has also interned here previously. If you're familiar with the Joule Meter project, she worked on that, and she's collaborating with some of you on other projects as well. So over to Nupur.
Thanks, Aman. I'm really excited to be here and talk about my contributions to simplifying the task of building robust and efficient network systems. So let's just get started. It's a well-known fact that network systems can be quite complex. Their functionality is distributed over multiple nodes, and they also have to deal with lots of issues like heterogeneity, network dynamics and failures, as well as application requirements like privacy, etc. Therefore, building such robust and efficient network systems can be quite hard. In addition, with the emergence of new domains like data centers, smartphones, and sensor networks, while these domains have brought in new applications, they've also brought in new requirements, which makes this task of building such network systems only more challenging. So the goal of my research is to develop practical tools to simplify the task of programming robust and efficient network systems. In my research, I've addressed various programming challenges faced by network systems developers. Let's first take a look at some of the challenges that I've addressed. So one of the most important programming challenges that a programmer faces while building a network system is that its functionality needs to be distributed over multiple nodes. For example, when a programmer is writing a smartphone application, she may have to try and partition the functionality of this application over the phone and this a cluster of servers in order to improve efficiency. Not only does the programmer have to partition this application, she then also has to worry about requirements like communication, coordination, etc. These and other application and domain-specific requirements form another challenge for network systems programmers. Here are some examples of various requirements that a programmer may be expected to handle. One important requirement is that of energy efficiency, which is crucial in the domains of sensor networks, smartphones, and data centers. Also, a lot of times, there may be a disparity between the functionality that the programmer had intended and the actual functionality of the code that they wrote. So, for example, the programmer may think of the functionality of a piece of code in terms of a very high-level representation, while that the code that they may generate may be very low-level. Hence, it may be difficult to try and detect such gaps between intent and actual functionality. Lastly, there may be potential vulnerabilities left behind in network systems code. These vulnerabilities can be really dangerous because then in a network systems, if we have malicious nodes, these nodes can exploit these vulnerabilities not only to improve their own performance, but also to do worse things like maybe crash other nodes or crash the entire system, etc. In my research, I have addressed these 4 challenges for various domains. My approach to addressing these programming challenges has been to develop and adapt program analysis techniques as well as build network system infrastructures for specific domains. And I've done so by leveraging domain knowledge from these domains. Most of my prior work has been in the area of sensor networks. I've built Pleiades, which is a programming framework to develop sensor network applications. FSMGen is a tool to extract high-level functionality from sensor network programs, and Hermes is a runtime interposition framework that allows the programmer to inspect the program state at a deployed sensor node. I've taken the lessons that I've learned from building all these systems for sensor networks, and I'm currently in the process of applying them to build solutions for other domains. I'm working on GuFi, which is a tool to detect vulnerabilities in code, and I'm also working on MobiProg, which is a programming framework for cloud-enabled cell phone applications. So first, I'm going to talk mainly about my prior work in the domain of sensor networks. I'm going to focus here on the work on Pleiades and FSMGen. After that, I'm going to spend some time discussing my work GuFi, which detects vulnerabilities in network protocol implementations. So let's start off with sensor networks. So what are sensor networks? Sensor networks are made up of devices which are small and battery powered, and generally we refer to them as motes. They sense the environment around them using various kinds of sensors, and they also talk to each other wirelessly. One important property that most sensor network devices share is that they are constrained in terms of memory, computational power, energy, as well as communication bandwidth. There are a variety of rich applications for sensor networks, ranging from volcanic activity monitoring to microhabitat monitoring to aquatic sensing and data center monitoring. In the case of sensor networks, unfortunately, the resource-constrained nature of most sensor network devices makes these programming challenges that I described earlier even harder to address. Firstly, most sensor network languages and operating systems promote an event-driven execution model. So one example of a sensor networking language and operating system is the Nessie TinyOS framework, which is also event-driven. Because of this event-driven model, what happens is that the code for these sensor network applications becomes more complicated, which makes these challenges harder to address. Also, debugging is really hard in sensor networks. Because of the resource-constrained nature of these devices, the regular mechanisms for debugging, like maybe logging, etc., become too resource-intensive. Hence, people have to come up with very low-level ways of debugging sensor networks. Testing before deploying is not good enough for sensor networks because sensor networks have a deep interaction with the environment, and hence a lot of times most bugs are not exposed while testing before deployment in a controlled environment. So, yeah.
In what sense are sensor networks special compared to, say, other embedded systems? These problems that you're alluding to, are they common to all embedded systems?
Yes, I think most of these problems are common to most embedded systems. I think the one thing here for sensor networks, of course, is that most of them communicate with each other wirelessly. And that adds another dimension because now communication is also a big constraint. So I've tried to address these challenges in my work. I've built Pleiades, which is a programming framework that distributes functionality over multiple nodes and that also handles many application and domain-specific requirements. Secondly, I have built FSMGen, which is a tool to extract high-level finite state machines from TinyOS programs. These finite state machines can help in detecting potential vulnerabilities in the code and can also help in determining what the differences are between actual functionality versus intended functionality. First, I'm going to talk about Pleiades. So in the conventional style of sensor network programming has been that programmers write node-level programs. Nessie is one of the most popular languages used in sensor networks. So these node-level programs are written from the point of view of a single node. They are then compiled into a mode binary and then installed over all the nodes. In Pleiades, what we propose is a centralized approach to programming, where the programmer writes a central program which can address the entire network as a single entity. This program then only needs to specify the application behavior. It is compiled using a Pleiades compiler to a node-level program, which along with the Pleiades runtime then is compiled to a mode binary. The advantage of this approach is twofold. Firstly, because we're specifying a centralized program, the programmer doesn't have to worry about distributing functionality over multiple nodes, and this is handled by Pleiades. Secondly, all the various domain-specific requirements of energy efficiency, concurrency, consistency, and failure recovery are offloaded to the compiler and runtime. So again, the programmer doesn't have to worry about handling these requirements. So at the time we built Pleiades, there were a few other sensor networking languages out there which were trying to do similar things. However, Pleiades is different in that most of the previous languages had a very restricted programming model or did not worry about requirements like consistency and failure recovery, etc. After Pleiades, a few other languages have come out which which have similar goals to Pleiades. However, these promote non-traditional programming models like data-force style programming or functional programming or declarative programming, while Pleiades promotes a very simple imperative C-style programming model. So let's take a quick example of what a Pleiades program can look like. So this is a simple example in Pleiades, which attempts to compute the maximum temperature over a network of nodes. As is obvious from the code, Pleiades is a simple dialect of C. Just by looking at this example, although admittedly this is a toy example, we can see that the readability is definitely improved by programming in a centralized fashion. And this is a piece of code that someone sitting at a desktop would have written. Now, what Pleiades provides is Pleiades provides the concept of a node local variable, where by annotating a variable as node local, the programmer effectively says that one instance of this variable exists at every node in the network. All the other variables are known as centralized variables, where only a single instance of such a variable exists across the network. Pleiades also provides an at operator, which allows one to access node local variables from various nodes. So here, temp at n basically means give me the value of the variable temp at the node n. In order to obtain efficiency, Pleiades allows for the programmer to specify concurrency using a C4 primitive. A C4 is basically a concurrent for loop. Yeah.
I'm confused. So all is not a procedure local variable? I would have thought that.
It is a procedure local variable, but it is a central variable in the sense that only one copy of this variable exists across the entire network. So basically, what that means is, if this procedure were to be migrated from node to node, then this variable would yes, exactly.
So it's not like there will be multiple copies of main running on different nodes.
No.
It's not like that.
No.
I see. Okay, no.
So it's a central program. You only have one program executing, and the way we get concurrency is by using this concurrent for primitive.
Okay.
Yeah.
What's the, what do you have I in that for?
What do we have?
Yeah, int I equals 0.
Oh, I'm sorry. It should have been n equal to null. Sorry.
Right.
That's a small edit.
And this get available nodes, does it have some semantic meaning? Is it a library function that says?
Yes, it's a library
the notion
function.
of a node, right?
Exactly. So Pleiades also provides the notion of a node, where node is a network node, and get available nodes is a runtime. It's a functionality provided by the runtime, where the runtime will figure out what the available nodes are and provide a list of those nodes. Yeah. Okay. So the property of this concurrent for loop guarantees is serializability.
Confused. Where does this main execute? Does it execute on every node? Does it execute on just one node at a time?
I'll come to that, but basically what it does is you move migration. You move the execution of this main function. But that's just the next thing I'm going to talk about. So okay, so concurrent for loop basically means that this for loop corresponds to some sequential execution of the loop iterations, although this execution may not necessarily be in order. So now that we've seen what a central program looks like, the main questions to ask are, how do the compiler and runtime actually efficiently execute this centralized program over a network of nodes? And secondly, how do we handle concurrent fors while guaranteeing serializability? So I think this is the question.
The semantics of concurrent for is that each iteration of the loop executes atomically.
It looks like it has executed atomically.
Even in the presence of, even if the different iterations are accessing shared variables and so
yes,
on.
Yes. So I know it's strict consistency that we're providing. Yeah.
Okay.
All right. Murray, how big can maybe I'm jumping ahead 50 slides here, but how big can a network scale? It seems like there has to be some, since you're programming in a centralized style, it seems like the network would have to be small enough to be able to apply centralized constraints, let's say, do centralized coordination to guarantee some of these constraints. I'm wondering how big can the network scale before this style starts to break down?
That's a good question. So I think, although we are programming in a centralized fashion, we have with the concept of concurrent for loops, we can actually run pieces of code concurrently on each node. So as far as that is concerned, scalability is not an issue. The problem comes when we're trying to guarantee serializability. There, yes, it is possible that beyond a certain scale, it may be hard to guarantee serializability, but then we can come up with other relaxed consistency mechanisms that can be guaranteed.
I guess it seems like if you're relaxing the consistency mechanisms, it seems like it might gut a lot of the semantics of your language, though. In other words, if the language says, let's say that the temperature acquisition is happening in rounds, then what we want to do is have everybody in the network sample it for one round and then do the comparison and then do the next round. Once the network gets to, let's say, multi-hop, then just being able to guarantee that these rounds are synchronous then imposes a huge overhead. And so I'm wondering, let me ask you a different question. How big have you actually implemented these networks yet?
We've done up to 50 nodes.
Okay, and all single hop or multi-hop?
Multi-hop. Okay. So going back to the challenges faced by the compiler in runtime, the first challenge is how do we efficiently execute a centralized program over a network of nodes? And the second challenge is how do we handle or provide concurrency for C4s while guaranteeing serializability? Lastly, how do we detect and recover from failures? So I'm going to talk in this, right now I'm going to talk about how the compiler in runtime handled the first two challenges. First, let's see how is a centralized program executed in an efficient fashion over a network of nodes. So here I take another even simpler example, which only consists of a sequence of instructions. And let's try to see how the Pleiades compiler in runtime would execute this program. Now, there are two extreme possibilities here. The first possibility is we migrate, we move the data to the computation. That is, we execute this program at a central location, and then we move the data to that location. The other possibility is we move the computation to the data. That is, every time we access a new variable residing at a different node, we migrate the flow of control to that node. Both of these strategies will result in high communication overhead and latency. So the approach we adopt is actually a mixture of both, in which we say that we do control flow migration as well as data movement. So what the Pleiades compiler does is that it statically partitions the code into smaller pieces of code called node cuts. The property that these node cuts satisfy is that the location of variables accessed within a node cut should be known beforehand. Now, the reason why these node cuts have this property is so that now, before a node cut executes, the runtime not only knows the location of all the variables within the node cut, it can then try to position the node cut in an appropriate fashion to improve energy efficiency and also prefetch all the variables required in the node cut to improve latency.
You use a subset of memory which disallows indirect memory access, meaning via pointers.
We don't really deal with pointers.
You don't use pointers, right? Okay, that's fine.
So, yeah.
So for what subset of the variables can you actually say that? Because you have an event-driven operating system, you're running a centralized program. At any given time, any node might want to access a variable, right? So for what fraction of the variables and for what fraction of time for each variable can you actually assume that you know the location of where this variable is going to be accessed?
So the location of the variable, so because we are writing a centralized program, it looks very sequential in nature, right? So I'm talking about the sequential parts. In the sequential parts, so the way we partition the code into node cuts is, before we, so a node cut, all the variables which are accessed within a node cut, we should know where they reside beforehand. Because, so here, for example, you can see val at n3, right? So what that means is that I should know what the value of the variable n3 is before I enter the node cut, so that I know where this particular variable resides. Because the assumption is that these variables are tied down to the nodes at which, to which they belong.
Variables will also be accessed by different nodes, right? Or I'm missing the point here. Each variable is owned by a single node?
Node local variables, yes. The centralized variables, we don't worry so much about the location of, because normally they will reside with the flow of control. Yeah.
Shouldn't you also take the size of the variables into account when doing node cuts? Or, I mean, if you have to end up moving code or data, one of the things you have to consider is
That's a good point. Yeah, we don't do that for now. We assume that all the variables are of the same size, but that's a good point. Yeah.
Handle failures. failures?
So I just said I'm not going to talk about that, but
sorry.
no, that's fine. But I'm sorry, I'm kidding. But basically, what the way we handle failures is we implement a rollback mechanism.
Okay.
So whenever we detect a failure, we try to roll back the computation that existed.
Okay.
Okay. So moving on. So this is how the compiler basically partitions the code into these node cuts. Now, the runtime, when deciding to execute each node cut, tries to figure out what is a good node to run the node cut at, so that the data is close by, and as well as the cost of moving the computation to that node is not too high. So in this example, it can be node N1. So thus, the runtime migrates the flow of control to node N1. Before executing the node cut, it also prefetches variables from nearby nodes that are required for the execution of the node cut. And then once it's done executing the node cut, it then decides where to execute the next node cut, and so on and so forth. The two questions here are, firstly, how does the compiler partition this code into node cuts? And secondly, how does the runtime know where to execute each node cut in order to improve efficiency? So let's first see how the compiler generates node cuts. So this is the control flow graph for the simple max example that I talked about before. Now, what the compiler does is it uses the property that the location of the variables accessed within a node cut should be known beforehand. So, for example, in the CFG node 4, we see that the variable temp is accessed at the network node N. While in CFG node 2, we see that this network node N is actually defined or given a value. So in order for us to be able to figure out where temp resides in CFG node 4, 2 and 4 cannot be in the same node cut. So the compiler introduces a split between nodes 2 and 4. So using this strategy and a couple of other heuristics that the compiler uses to maximize concurrency, what we try to do is we develop an algorithm to minimize the number of edges cutting across node cuts. Intuitively, why we want to minimize the number of edges cutting across node cuts is because each edge effectively corresponds to a migration of the flow of control. And we want to minimize this migration because it incurs communication cost, and hence we try to minimize this. So for this example, the Pleiades compiler generates these following node cuts. Now that we know how the compiler generates the node cuts, let's see how the runtime actually figures out where to run each node cut. So like I mentioned before, the runtime tries to find the lowest communication cost node to execute the node cut. For this, again, it utilizes the property that the location of variables is known beforehand in a node cut, and assuming that it has topological information, it can actually try and figure out exactly where to run the node cut in order to minimize communication cost. And this communication cost consists not only of the cost of prefetching variables, but also the cost of migrating the flow of control. Okay. So next, let's see how does Pleiades handle C4s and guarantee serializability.
It seems like the topology needs to come into account there somehow.
Yeah.
Are you going to talk about that?
I was not going to talk about it, but basically, so we assume either that you have a topology, or we don't even need a topology. We just need some form of some cost metric by which we can say that this executing something at this node is actually more costlier than executing the node cut at some other node. So we don't really need like the entire network topology, but just knowing about its neighbors and nearby nodes should be good enough.
That's not done that's done by the runtime, I'm assuming, not.
That's done at runtime,
Okay.
yes.
And so I guess the runtime then has, let's say, a path discovery mechanism or something, and it's updating its costs based on how far away the nodes are, or?
Yes, yes. So for the experiments that we conducted, we actually used static topology. And so for that, of course, the answer is easy. But if you wanted to do it for a dynamic topology, then you would have to have a path updating mechanism by which you figured out how many hops away each node was, etc., and what the cost was. So talking about serializability. So serializability is a concept that's often used in databases, and in our scenario, what it means is that the outcome of a C4 execution should be equal to the outcome of its iteration executed sequentially, although not necessarily in the same order. So the challenge here is, how do we guarantee serializability while still providing some concurrency? And our approach to do this has been inspired by the strong, strict two-phase locking approach. Yeah?
And you assume that we don't have nested C4s?
We do assume we can have nested C4s.
You cannot?
We can.
You can. And what
Yes.
is the semantics in that case?
So the semantics in that case is that each level of nesting is serializable, and then so each level of nesting is serializable with each other.
So it's like, so if you, let's say the outer loop goes m times and the inner loop goes n times in each outer iteration, then you have mn iterations, and you are going to guarantee serializability of those m times n blocks?
No, we are going to get the serializability of the n iterations within the inner C4 loop, and then once those have been those have completed, then we are going to get the serializability of the outer.
So it's like you flatten the inside guys.
Yes,
to one
exactly,
block. Okay.
exactly. Yeah, and so the way we do that is by using the strong, strict two-phase locking approach, where we can have multiple readers and a single writer. Also, in order to be able to deal with nested C4s, we've developed a hierarchical approach, a hierarchical version of this approach. What this approach buys us is, firstly, only write operations to variables require serial access. So if C4 iterations are only accessing, are only reading variables, then they can proceed concurrently. This approach guarantees us the property of strictness, which allows us to build an efficient deadlock detection and recovery mechanism. Also, all of this locking, deadlock detection, and recovery code has been generated completely by the compiler and does not require any inputs from the programmer. So moving on to the implementation, we've implemented the Pleiades compiler as an extension to SIL, and we've implemented our node cut algorithm over the SIL data flow framework, data flow analysis framework. The Pleiades compiler generates NestC code, and we've evaluated it on TELUS-B motes. We've implemented a couple of different applications using Pleiades, two of them being street parking and pursuit evasion. So next I'll talk about the performance of Pleiades with respect to these applications. So street parking is a simple application where we envision that a sensor node is placed at each parking spot on a street, and it basically maintains a record of whether the parking spot is empty or full. So now when a new car comes in, it can ask the closest sensor node to find it an empty parking spot, and then the sensor network will find an empty parking spot and direct the car towards that. So here we've implemented a street parking application over Pleiades. On the x-axis, we have the request ID of the various cars coming in and asking for new parking spots, and on the y-axis we have the latency of satisfying each request. So we implemented a basic version of the street parking application with the Pleiades runtime, which had no locking. And for this, we found that the application does not execute correctly, and the last few requests cannot be satisfied if we don't have locking. On the other hand, for Pleiades with locking, we found that the application executes correctly and is able to satisfy all the requests. Now, we also implemented another version of the street parking application with induced deadlock. So we induced a deadlock in the application, and we ran it for a version of the Pleiades runtime which did not have deadlock detection and recovery. In that case, we found that after the first request itself, the application got deadlocked and then crashed. Yeah?
By incorrect execution, you mean there are concurrency errors?
Yes. Basically, what happens is that two spots are assigned to the same car. And so what happens is that then, at the end, when new cars come in, all the spots show that they're busy when they really are not. So we tested this version of the street parking application with the induced deadlocks for Pleiades with deadlock detection and recovery. And I forgot to mention that in the case of correct execution with locking versus the case of incorrect execution without locking, the difference in latencies is not much, leading us to believe that the locking overhead is small. Also, so moving on to the case with induced deadlocks, we found that we actually, the application performs correctly, managing to satisfy each request. Again, in this case, the difference between Pleiades without deadlock detection and recovery and Pleiades with deadlock detection and recovery is not much. Hence, the deadlock overhead is also small compared to the benefits it gives us. An interesting thing to note here is that the latency is a little high to satisfy each request. And that's actually an implementation artifact, not really a result of the design of Pleiades. It's basically because we were using a very unoptimized transport layer, and if we replace that transport layer by a better one, then these numbers should improve. Yeah.
So let's say I program this application using my event-driven programming model, which is say NestC. Then at some level, all the complexity you're hiding inside your abstraction would have to be dealt with by the programmer, right?
Yes.
But in that case, most likely the program, if the programmer managed to construct a correct program, it would be more efficient.
Yes.
Right? So did you actually do a performance comparison? Meaning, what is the hit you're getting in performance because you moved to this higher level of abstraction?
So the problem is that for street parking, we actually found it very difficult to write an SC program because the amount of consistency that is required is very high. So we've done this comparison instead for a different program application, which I'll talk about next, which is pursuit evasion. So pursuit evasion is an application where we have two robots. One is a pursuer and the other is an evader. And the goal of the sensor network is to try and locate the evader so that the pursuer can then catch the evader. And we implemented a version of this in Pleiades, and we compared it to a hand-coded version in NestC that others have written, not us, but someone else. And what we found was that, yeah, lines of code, Pleiades obviously does really well. But surprisingly, for the other metrics as well on which we compared it, Pleiades does surprisingly well. And it's respectable. Latency is a little high, but then again, that's due to the unoptimized transport layer that we're using. So that's there. But for everything else, Pleiades does respectably well. And so we found that Pleiades can actually successfully reduce code complexity while providing acceptable performance and efficiency. Also, all these requirements of consistency, synchronization, and failure recovery are handled by Pleiades, and the programmer doesn't require to intervene in those. So now that I've talked about Pleiades, yeah?
About power?
What about it? Power?
Yeah, go back a slide.
Okay.
Right? I mean, power is the dominant issue on...
Yeah, so we try to do this in an energy efficient fashion.
What?
We do try to do this in an energy efficient fashion.
I guess my question is, so what's the difference?
The comparison?
Yeah, I mean,
so,
should I just look at the message overhead and power it's going to, so it's...
Yeah, I think a message overhead is probably a good approximation.
So anticipate it'll be 50% more power.
Yeah.
So you mentioned failure recovery. I'm sorry to go back to this, but so this is the rollback mechanism that you were talking about before?
Yeah.
I guess I wanted to push a little bit more on that because it seems like failure is such a common case.
Right.
And the semantics are so different across applications. It's not something that you can just sort of push under the rug. For example, if a node just dies, then you can't execute that loop anymore because you just won't be able to contact it. So do you just forget about it, and then if it comes back in, do you deal with it again? Or it seems like failure.
So we have two things here. The first thing is the node executing an iteration, C4 iteration dies. In that case, what happens is that this is detected, and the computation at that node is rolled back and executed at another node. The other possibility is the node where some data is residing dies, which is worse because now we don't have access to that data. In that case, we just have to declare that iteration, that particular iteration, to have failed because there's no way to recover from such a failure.
So if a node dies, does that mean the system makes no further progress?
So if a node dies and it doesn't have any data that is required by the system continues to make progress. In case the node dies and it has some data that is required, then what happens is that particular iteration does not complete. And so the C4 realizes that one of the iterations has died because of a node dying, and so decides whether it wants to move on and continue progress further on, or does it want to declare failure at that point.
I guess you showed a loop in your toy example that said we wanted to compute the maximum temperature.
Right.
So we collect temperature from every node and then find the max. So if one of the nodes dies, it will never succeed in every single time you go through that loop. Is it still going to try to get data from that node and then fail, and then the loop fails? Or
No, we just maintain a list of nodes that have died.
Okay,
so basically, every time the first time the loop occurs and we figure out that the node has died, what we do is that we just abandon that particular iteration and we continue the computation. And so at the end, what will happen is the maximum value that will be generated will be for the rest of the nodes, not for the node that has died.
Okay.
So basically, in this case, so this is the semantics of your programming language. That in the case of a node failing, it's as if that iteration did not happen at all. Is that so? What I'm asking is that, like, the idea that trying to compute the max of n numbers, but you only compute a max of some subset of them, that is the semantics. That is the expected semantics of the program.
Yes, if the node dies, then that is what even a sensor network programmer would do, which is if a node dies, you don't have access to the data at the node, you would just ignore it.
I mean, what if I wanted to write a sensor network program which wanted to detect that a node has died, and in that case sent a message to some centralized control station saying, oh, send somebody over there, do some fixing or something? How would I program that?
So actually in this we do have a mechanism by which we can detect that a node has died, and so one could imagine exposing that to at the programming level, saying that okay, a node has died and this is a particular iteration, and the user can then handle that failure in whatever way they see.
But your current programming model does not expose that.
No.
Okay.
But definitely it's a possibility. Yeah. Okay, so I'm going to move on, and next I'll talk about FSMGen, which is a tool to extract high-level finite state machines from TinyOS programs. So the motivation behind this is that most programmers, when they write event-driven code, they tend to think in terms of finite state machines, because finite state machines actually match up really well with the structure of event-driven code. However, the code that they generate can be really complicated, and so it will be nice if we could have a high-level representation of this code that the programmers could then match what they had thought about the functionality to be, and then look for where the actual functionality differs from the intended functionality. Also, having such a high-level representation would help in locating potential vulnerabilities in the code. So what we've done in FSMGen is, given a TinyOS program, we've built a tool that from this TinyOS program can extract a compact, human-readable, high-level finite state machine. So finite state machines the concept of finite state machines has been used before in sensor networks. However, finite state machines have been used more as people have designed languages based on finite state machines to program sensor networks, and people have also built finite state machine specifications for various interfaces in sensor networking languages. Program analysis has also been used as a tool for sensor networks, however, for specific tasks like memory, safety, etc. Lastly, there have been tools to derive finite state machines from programs in regular languages. However, these finite state machines were intended more to be intermediate finite state machines that were fed into other model checkers or other verifying steps. So I believe that FSMGen is unique in its goal of trying to find a human understandable, compact finite state machine given event-driven TinyOS program. So what are the challenges in building a tool like this? The first challenge is, how do we statically obtain information about the execution of a program? Secondly, how do we distill this information to form a finite state machine? And lastly, how do we ensure that the inferred finite state machine is compact and human understandable? So we address these challenges by taking certain techniques from the program analysis community, programming languages community, and adapting and modifying them for event-driven programs. We use symbolic execution to obtain information statically about the execution of a program, and then use predicate abstraction to take this information and generate a finite state machine. Lastly, we've built a variant of the Mihail-Nerod FSM minimization algorithm to ensure that the inferred finite state machines are compact and user understandable. So let's first take an example of what a finite state machine would look like in TinyOS NestC code. Now, so here I've elided all the NestC and TinyOS specific details so that the example is a little more readable. But this is an example, this is a piece of code that a lot of sensor network programmers would actually be very familiar with. Like I mentioned before, debugging is really hard in sensor networks. So a lot of people, what they do is that for debugging, they use this very simple mechanism of checking program state within their code and turning LEDs on and off depending on what the program state is. So they do that in their code, and then when the program is running on a sensor node, they just sit back and observe the sequence of LEDs to figure out what errors are happening on what execution path the program is taking. What this example does is something very similar. What it does is it says, well, if I receive a message and if the value of the received message is less than 5, then everything is okay, and I turn the red LED off. But if the value is not less than 5, then I turn the red LED on to maybe indicate a problem or to indicate everything is going, something is wrong. So let's now try and see what a finite state machine for this example would look like manually. So finite state machine for this would have 3 states. One is the initial state, where we don't know what the state of the red LED is. The other 2 are states where we know that the red LED is either on or off. So if this message received event occurred and the value of message was less than 5, then the state machine would transition from the initial state to the state where the red LED was turned off. On the other hand, if the value of message less than 5 was false, then the state machine would transition to the state where red LED is turned off. For now, I'm not going to look at scenarios where you can have multiple occurrences of the same message received event handler, but assume that this event handler can only occur once. So this is the simple state machine that is represented by this snippet of code. Now I'm going to talk about FSMGen, how it works, and what finite state machine it would generate for this simple snippet of code. Yeah.
Your goal is to generate a finite state machine for an individual event handler?
No, for the entire component.
So which can have lots of event handlers.
Yes.
So the model you generate is going to capture the causality between an event handler executing and generating further events that are going to trigger other event handlers.
Yes.
Okay.
Yes.
Good.
Okay. So although I will not talk about that in detail too much. So next, let's take a look at the overview of the FSMGen system. The main module in the FSMGen system is the FSM generator, which takes as input a TinyOS program and a concept of interesting modular events that the user wants to study in detail the functionality of within the TinyOS program. This FSM generator uses a symbolic execution framework and predicate abstraction module to generate a finite state machine, which is then minimized by the FSM minimizer to give us the final output, which is a user-readable, compact finite state machine. So now, going back to the debug example that I presented, let's try and see how each individual component works for that example. So first we use symbolic execution to statically extract information about the execution of a program. So symbolic execution is a simple program analysis technique where rather than providing concrete values to program inputs like, let's say, 1, 2, or 10, we provide symbolic values which can represent any arbitrary values. Using these symbolic values, we then track all possible paths of execution through the program. At each point, we maintain a mapping from variables to the actual symbolic values, as well as what were the assumptions that needed to be made about these symbolic values to reach that particular program point. So in our example, debug example, what this would mean is that when we encounter, for the message received event handler, let's say a symbol beta would be assigned to the input message. And then we would track the execution of this event handler using the value of message being beta. At the end of the execution, we could have 2 potential symbolic program states. One in which beta less than 5 is equal to true, and that means that red LED was turned off and red LED is set to false. The second being the state where beta less than 5 is equal to false, which means that red LED was turned true. So this is how symbolic execution takes a program and generates all the possible symbolic states at the end of execution. Now, in predicate abstraction, we take the symbolic state and convert it into a state in the finite state machine. So in this scenario, a finite state machine state is basically a valuation of a set of predicates. This set of predicates is actually derived from the program code itself, and in this case, it ends up being the 2 predicates, message less than 5 and red LED. So predicate abstraction derives what the value of these two predicates is by looking at the symbolic state, which in this case turns out to be true and false. So this is how predicate abstraction works. All of this is put together by the FSM generator. What the FSM generator does is that first it symbolically executes the main function of the program to get what the initial state of this state machine should be, which in this case turns out that both of these predicates are unknown. It then keeps track of what are the events enabled. So here in this case, the only event that we're looking at is the message received event. And so it symbolically executes that and then adds the resulting finite state machine states to the state machine, where on the edges it puts not just the name of the event, but also the assumptions that needed to be made in order to end up in that particular state. So this is how FSM generator generates a finite state machine. It continues this process, of course, until no new states or edges are added. And here it basically handles, keeps track of what events are enabled and when they can be triggered or not. So it's interesting to note that this finite state machine is actually the same as the finite state machine that we had manually derived. For this case, because it is such a simple example, we didn't have to worry about minimizing the finite state machine. So because this was such a simple example, there were a lot of things looked really simple. However, to get it to work for actual real TinyOS applications, there were a number of challenges that we had to handle. So firstly, we had to adapt symbolic execution for event-driven programs. This involved handling and tracking various events, when they occur, what they are triggered by, and also dealing with asynchronous function calls. In TinyOS, we have a concept of asynchronous function calls called tasks, where you post a task and then you forget about it, and then it executes whenever event handlers have finished executing. So we had to deal with those. We also had to deal with this concept of split phase function calls, which are basically pairs of calls and events in TinyOS, where a call somehow triggers the ensuing event. An example is the send and the send done pair, where the function called send basically asks the radio to send out a message, which then triggers a send done event from hardware, which indicates that the message was sent out correctly. So tracking the functionality of this can be quite tricky. So we deal with this as well. Also, we have to try and reduce computational complexity without compromising on accuracy. In order to do that, we have a concept of interesting modules, where we say that the user can actually specify what are the modules that he wants to focus on or know the details of the functionality of, so that we can abstract away the lower level details from the other modules. Also, we build a very coarse-grained execution model for TinyOS, which, while reducing computational complexity, still provides good accuracy. Lastly, we have to deal with minimizing finite state machines for many applications. So we've implemented FSMGen over the SIL framework, and we've used the CVC3 constraint solver in our implementation. We tested FSMGen for a number of different TinyOS applications and system components, including version 1 of TinyOS as well as version 2. We found that of all the finite state machines that we generated, the maximum size was 16 states. And this was for a very complicated protocol, a time synchronization protocol called FDSP. We were able to highlight two inconsistencies in various components, surge and multi-hop engine, using the generated finite state machines. Next, I'll show what was the finite state machine generated for surge and what was the inconsistency that we found. So surge is a simple data collection application which periodically polls the sensor and sends the value, routes the value to the base station. So we manually verified the functionality of this finite state machine is actually the same as that in the TinyOS component. An interesting thing to note here is that once the execution transitions from state 2 to state 4, it seems like one would be in an infinite loop between states 4 and 6. These are basically error states, indicating that this doesn't seem right. So I went back and looked at the code and found that the state machine is correct. The reason why surge people haven't complained about this while using surge is because this transition between 2 to 4 depends on the way an underlying interface is implemented in TinyOS. So in practice, it is never taken. However, if that underlying implementation were to change, then this edge definitely could be taken, and this would result in a bug.
Your model generation was able to detect this edge because you modeled that underlying interface in a very general way?
Yes, because we abstracted away the details of that. Yes. And so we were able to get this edge. However, in reality, this edge is not taken because of the way that interface was implemented. So up until now, I've talked about Pleiades, which is a centralized framework for building sensor network applications, and which handles a lot of these application and domain-specific requirements and manages to reduce code complexity while providing acceptable performance. I also talked about FSMGen. Yeah.
You caught an error because you had modeled the interface in a very general way.
Mm-hmm.
Does the opposite ever happen, that you miss certain things because your interface model is too simple and it misses certain subtleties? Or
it's definitely possible. We haven't seen that, but it is definitely possible. In that case, if it seems that the error would lie within that implementation of that interface, and so the programmer would then have to change the focus to that interface. If that was specified as an interesting module, then that would show up in the finite state machine. So the way this abstracting away of details is sort of controlled by the programmer when, or the user when they say that, okay, these are the modules I'm interested in looking at the functionality of. So if they want to look at that functionality as well, then it would show up. So I talked about FSMGen, derives compact finite state machines, and we find that these finite state machines can sometimes also point to inconsistencies in code. Next, I'm going to talk about GuFi, which is some ongoing work that I've been involved in with people here at MSR, and which I'm really excited about. And let's move on and see what GuFi is. So GuFi, or Gullibility Finder, is a tool that for a given network protocol implementation modifies incoming messages at a node to try and repeatedly drive the execution of the implementation down to a particular interesting statement. So this interesting statement, for now we assume, is specified by the user of this tool. So an example could be, in the TCP implementation, the user may specify that all statements that increase the congestion window at the TCP sender are interesting statements. And GuFi would try to find mechanisms of modifying incoming messages at the TCP sender to try and get the implementation to execute these interesting statements. So the goal of GuFi is, firstly, how do we modify these incoming messages to trigger execution of these interesting statements, and whether it is even possible to modify messages in such a fashion. And secondly, can this manipulation be used by malicious or selfish participants to improve performance? So intuitively, if these interesting statements are statements that allocate some form of resources to a particular participant in the protocol, what would happen is, if you repeatedly can trigger these statements, then the resources allocated to that particular participant would increase, and then that node would actually benefit. Yeah.
I have a question about the problem statement in the first bubble. In particular, no, go ahead. Go forward. Why do you use the word repeatedly there? I mean, you just want to find one modification of the input message that it can reach that particular statement once, right?
No, we want to be able to do it every time for each incoming message, or for a large chunk of the incoming messages. Because the idea is, we're looking for these sort of resource attacks where, they're very subtle in the sense, if you modify one message, you may only get a little bit of a benefit. But if you can do it repeatedly, you'll get a lot of benefit. So we want to be able to do this repeatedly.
Here then lies in finding the interesting statement, not about how to trigger the first part of that question seems to be, and correct me if I'm wrong, I'm not an expert in this, it seems like it's a test case generation problem, right? Which is, there are so many solutions to potentially. It's the leap from the first statement to the next statement that's the challenge, which is these interesting statements result in some sort of interesting behavior, right? And how do you find that given a protocol spec?
Right, but I think that even the first part is also challenging, because it's not just about finding one case that works, but being able to do it repeatedly. That is interesting to us. And yes, I mean, finding interesting statements, of course, leads us to discovering these mechanisms, but hopefully the number of interesting statements should be small enough, because we're looking only at resource allocation statements. So, so effectively, you're sort of moving the complexity. While it is still challenging to find these statements, you're effectively moving the complexity of finding an actual attack or the mechanism for an attack to the tool. And we want to do this repeatedly.
If you get this allocation statement repeatedly, then you can launch a denial of service attack, something like that, because you can create so much memory consumption or something.
Right,
like
not just a denial of service attack, but even more subtle attacks where, let's say, the user is the malicious node is selfish and wants to improve its own performance. So if that's the only thing that interests it, it doesn't care about what happens at the receiver. That's something that's very hard to detect because you're not really hurting the receiver in any way. What you're doing is you're extracting more performance than is fairly your share. So the second question, of course, is how can this manipulation be used by malicious and selfish participants to improve performance? So we've built an initial prototype of this tool, GuFi, and we've used it on TCP. And I'm going to explain how GuFi works using the TCP example. We've used a user-level implementation of TCP called Daytona. And in this case, our goal is to see whether the TCP sender can be manipulated in this fashion. So we want to analyze the code at the TCP sender. And the interesting statement that we provide to it is any statement that decreases the number of outstanding packets at the sender. So intuitively what this means is if I decrease the number of outstanding packets at the sender will send out more packets towards me because it thinks that I've received all the packets that it's already sent out. And so if what this will do is it will give me a better throughput than I would have gotten otherwise. So for this particular example, let's see how GuFi works. So GuFi has two parts to it. The first is the program analysis part, and the second is the testing phase. In the program analysis phase, GuFi uses symbolic execution to take as input the TCP code as well as what the interesting statements are and generate a list of potential paths that can lead to interesting statements. Also what it does is it generates a module which tries to emulate a malicious receiver, TCP receiver. In the testing phase, we run the original TCP implementation at the sender and the receiver. What we then do is we assume, so here the assumption of course is that the sender is the honest guy, and we're trying to see how the receiver can manipulate the sender. So we then execute the module which emulates a malicious TCP receiver in the middle. So in this setup, whenever the TCP receiver sends out an acknowledgement message to the sender, it is intercepted by this module. This module then takes global state from the TCP sender and also takes the list of potential paths that we had generated that lead to interesting statements and figures out how to modify this ACK packet in order to trigger one of these interesting statements. It then sends back this modified ACK to the TCP sender. And we measure this, the performance for the receiver in this setup with the regular setup where both the sender and the receiver are honest. And here I forgot to mention, we actually, for now, we also restrict what particular fields of the message can be modified by the malicious receiver. So for this, we actually performed this comparison using GuFi for Daytona, and we found that the malicious receiver actually does pretty well. So on the x-axis, we have the time, and on the y-axis, we have the sequence number of the packets sent out at any given time. We can see that for a particular time, the malicious receiver succeeds in getting the sender to send out a lot more packets than the honest receiver. When we looked at exactly how GuFi modified the TCP ACK packet, we found that what it does is that it modifies the ACKed sequence number in the ACK packet. So it increases the sequence number that has been ACKed in the ACK packet. So this is actually the optimistic ACKing attack, which was introduced by Stefan Savage and others in '99. So GuFi, effectively, by being provided with the protocol implementation and an interesting statement, can actually provide us with the mechanism of a particular attack.
Is it correct to say that this particular attack can only slow down the network? It doesn't have any sort of safety. It doesn't produce a safety violation in what the TCP protocol is supposed to do. It's only going to lead to a performance problem. Is that right?
Yes, but I mean, it can lead to severe performance problems. In fact, yeah.
But I was just trying to understand what's going on.
Fairness? Is this a fire?
It violates fairness. It can cause denial of service attacks. In fact, this particular attack has been documented in the US CERT database of gullibilities or vulnerabilities as being an attack that can cause network failures, etc. So, yeah. So GuFi is still ongoing work. I'm still working on it, and I'm really excited about it. I think GuFi can prove to be a valuable tool for designers to explore implementations for gullibility by simply providing a hopefully very small set of interesting statements that govern the resource allocation of resources like airtime or number of packets that are outstanding, etc. I believe GuFi can be used to detect other protocol gullibilities in TCP as well as 802.11. I'm really excited to see if it can actually find attacks which were not known earlier. Also, GuFi can be extended to deal with more complicated attacks, where we have multi-step attacks, where we have each step the user wants to do something very specific. We can also have packet injection attacks, where rather than simply modifying the incoming packets, we actually inject new packets into the system. And lastly, we can have multiple attackers trying to collude together to cause to attack a single node. So now that I've talked about GuFi, let me talk about some of my,
I know that Don Sung's team has been doing some work where they look at input files to programs and they do static analysis back.
Yes.
Other than the fact, is the main difference that it's network packets that are the input rather than?
Well, so that is one difference. We're studying a particular aspect of the implementation. They actually, from what I know, they use binaries. They analyze, they don't analyze actual source code. And the other thing is they're looking for very specific kinds of, yeah, that's true. But we're focusing on a very, so TCP can be a really big protocol. And they do it, so we're focusing on a very small aspect of that. And I think the other thing, though, is that they're not looking for these sort of subtle attacks. They're looking more for attacks which can, I think, crash the machines, etc., like at a particular node. So in the future, so like I mentioned already, I'm working on MobiProg, which is a tool to build cloud-enabled smartphone applications. And the challenge here is to figure out how to dynamically partition a smartphone application between the phone and the cloud so as to minimize energy consumption and delay while still providing guarantees for privacy, etc. I'm interested in the future to continue to work in the area of smartphones and look at other kinds of smartphone applications where you have multiple smartphones interacting with each other, like multiplayer games or collaborating sensing applications. Another area of interest is building tools to find vulnerabilities in third-party smartphone applications. So this is becoming a real problem even for current users because a lot of smartphone applications have come out which are malicious in that they try to steal private data from smartphone users, or they simply just drain the smartphone of batteries. And being able to detect this using some program analysis or runtime techniques would be nice.
How do you do that? That's fascinating. How do they drain a smartphone of its battery?
You just run some computation, which takes up a lot of memory, and that's it. Yeah.
Why would I even download some random application?
So I assume you're not talking about iPhone apps, or are you?
There have been iPhone apps which also do that, right? But now, of course, I think it's become stricter, and they're being thrown out of the app. But yeah, I mean, I think Android, Windows Mobile, you can have a lot of applications. Yeah, actually, there's also this sleep cycle monitoring app, which basically, I mean, I think the fact that they drain your battery is unfortunately a side effect of their functionality. So you're warned to actually keep your phone connected while you're using the application to ensure that your phone doesn't die. But it is possible that people may do this maliciously, or it may just be a bug in their code.
So you power, you also listed privacy and security. So are there iPhone apps that you would put in those two categories?
Actually, So as far as the iPhone goes, I did hear of one case where a game developer was sued because they supposedly were downloading their users' phone numbers and storing them, which was violating privacy concerns. So there are still scenarios. I think in the iPhone, because of the strict restrictions they place, it's harder. But on the flip side, for developers who are building applications, for developing for the iPhone is very hard because you're not provided the rich interface that, let's say, Windows Mobile or other platforms provide you with.
Which explains why they have so few iPhone applications. And conversely, why there are so many smartphone applications. Yes. I buy your hypothesis.
Okay, so moving on, I'm also interested in building tools to develop efficient data centers. So while I was at MSR in summer 2008, I worked on a runtime profiling tool that actually tried to profile the energy consumption of individual processes on machines. And a lot of people have been using such tools to actually do energy-aware scheduling of tasks for data centers. So what I'm interested in is seeing whether program analysis can help in this in some fashion. So to conclude, well, I talked about why building network systems is difficult and listed some of the challenges that programmers face. And then I talked about the tools that I've built to address these challenges for different domains, which include the tools I've built for sensor networks, as well as the tools I'm currently working on for protocol implementations and smartphones. In the future, I'd like to continue to work in, for these directions, as well as explore other domains which pose interesting challenges. Thanks.
I got a question about your GuFi work.
Okay.
So you made it sound as if you built the system, and lo and behold, you got an attack out of it, and then you suddenly discovered that, oh, somebody actually wrote a paper a few years ago which was exactly this attack. Is that the real story, or were you actually trying to find that attack?
So we built the system for TCP.
Okay.
At that point, we did not have any attacks in mind.
Okay.
Of course, we had to look at what are the attacks possible for the implementation that we were using, but that helped us in identifying what the interesting statement could be, but that did not change anything else. GuFi ran as it is for everything else.
So you were not aware of that specific attack by Savage when you actually started GuFi off trying to look for an attack which is trying to find, this reducing this the counter.
Thing.
Okay.
Yeah.
Can I ask a snide question, admittedly very snide question as a follow-up on that question? How is it that every attack you have found so far has been discovered by Stefan Savage? Even the Wi-Fi attacks that
Coincidence.
So I have one more question about the GuFi work. It's very interesting. So you mentioned that the thing in the middle, which is takes as input the current packet, the list of paths, and the current state of the sender or the receiver, one of them, right?
Right.
And then tries to figure out how to perturb the packet. So the state component that is fed as input, is it easy to get a handle on all the state that could be pertinent to the TCP stack at a particular machine?
Right. So actually what we do is we look at the list of potential paths that we've generated to figure out what is the state that is useful to us. So we don't take all the state from the TCP stack. We only take the state that helps us decide which path to take, or that is crucial in getting us to hit the interesting statements.
So you basically just read that state from there.
Exactly.
Oh, that's very nice.
Yeah. So I mean, one thing I guess I didn't talk about, or I sort of glossed over, was the fact that this malicious receiver is actually running at the TCP sender in our testing phase, because we found that it was much easier to import global state and do other things at the sender itself.
But, I mean, the TCP state is nicely encapsulated in the TCP, right? So you could just leave that entire TCP structure, and there's no need to go look around for anything special.
Well, but the reason is we don't want to, I guess, because even in the TCP structure, there's so much state, right? We don't want to read all of it. We only want to read the particulars that are relevant to us.
And how big is the code in the TCP sender that you had to analyze to generate that list of paths?
I don't know how many lines of code, but basically it's the kernel TCP just ported to user level.
So actually, I have no idea.
It's huge.
So are we talking like
thousands and thousands and thousands of lines?
Like hundreds of thousands, you mean?
I don't know about hundreds of thousands. The problem is that the basic TCP protocol is what it is, and there are a large number of variations that people have proposed. And the Windows TCP stack supports a large number of standardized variations. That's what creates. I don't know what daytona supports. But
so we actually used a very simple. We used only one of the congestion control mechanisms that are support from all that are supported, but the code was still huge. And symbolic execution, actually, we're facing scalability issues with TCP.
With the verified that the TCP protocol, Microsoft TCP protocol stack was correctly implementing certain RFCs, and even the very basic version, it took them something like 3 years of CPU execution time or something crazy like that.
Okay, thanks.